Hi everyone. Today we're going to look at solving linear quadratic systems of equations. So last year in grade 9, what you would have looked at is probably graphing two lines and then finding what we call the point of intersection. Or you would have solved it algebraically. So you would have solved it either with substitution or elimination. So hopefully that's all kind of coming back to you, ringing a bell. But that's all it really is. It's these two lines that you have, and you're trying to find that point of intersection. So we're going to do the same thing today, except we're going to take a look at one is going to be a line, and the other is going to be a parabola. So that's how we're going to change it up. And let's take, for example, this is our parabola. And I want you to think about this question, so maybe pause the video. What are the possible ways that a straight line can interact with a parabola? So you should think about that for a minute and then pause the video. And now maybe you're back, and let's take a look at all these different ways. So I'm going to grab, I think green here is pretty nice. So we can definitely have a line that cuts straight through our parabola, giving us two points of intersection. So there can be 2 points of intersections, 2 POIs. We could have, maybe it only touches it like once, like just nicks it there, like that. So it could have 1 point of intersection. Or maybe my line goes underneath it like this and will never actually hit it. So we can have 0 points of intersection. So those are our 3 options when we have a quadratic. It will either cut it twice, it'll cut it once, or it won't even touch it. So 2, 1, or 0. So on our next slide, we have just kind of a diagram here. If you have a line that cuts through a parabola, it's called a secant line. And if you have a line that only touches it once, it's called a tangent line. So those are just the official names of both of these, secant line and tangent line. There is no name for a line that doesn't touch it at all, okay? Just doesn't touch it at all. All right, so you may want to just pause the video here and copy this slide out. And then once you're done, let's go to the next slide. So here are our notes on it. This is it. So it's not very big and long, but it just tells us that at most it can intersect twice. So we can have 2 points of intersections. That's most we can have. One of the functions will be quadratic. The other will be linear. And to determine our points of intersection algebraically, we use substitution. So substitution was something that we saw last year in grade 10. We're going to replace our f of x with the quadratic function with the expression for g of x from the linear function. So I'll show you what that looks like in just a moment. What you end up with is a quadratic equation whose solutions correspond to the x coordinates of the point of intersection. So we're going to solve for x is what we're going to do. So pause this here if you need to keep copying. If you're done, then let's move on to the next slide. All right, so we're just going to do some examples. Determine the coordinates of the point of intersection of the parabola and the line. So the first way that we can do this is through a graph. And this definitely, if you're very good at graphing parabolas, this could definitely work. Y equals x squared minus 2 is a parabola that opens up, starts at -2, and then it follows our 1, 3, 5 pattern. 1, 2, 3, 4, 5 up here, over 1, 1, 2, 3, 4, 5. Again, if you're not good at graphing parabolas, that's okay, because I'm going to show you another way on the next slide, which is actually a better way of solving. But you could graph it, but if you're going to graph it, you have to be precise. And then I'm going to graph my linear. So my linear has a y-intercept at 1, and then it has a slope of 2 over 1. So that means, remember, rise over run. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, or down 2 to the left 1, down 2 to the left 1, and I get this lovely line right here. And then it's easy to see where my points of intersections are on this because it worked out so nice. So I have one point of intersection at -1, comma -1, so that's the one down there. And then I have another point of intersection here, which is at 3, comma 7. So you could definitely go ahead and graph. But again, you have to be precise. So it's not sketching, it's actual graphing, and then seeing where the line actually cuts a parabola. All right, so what if graphing is not our thing? So, and there's many of these where graphing is not our thing. So for example, y equals 2x squared minus 5x minus 3, and y equals -9x minus 5. I do not want to graph either one of those, actually. So what we're going to do is we're going to say, since y is equal to this expression and y is equal to this expression, it must mean that those two expressions are equal to each other. So 2x squared minus 5x minus 3 must also be equal to -9x minus 5. So we're going to take our two expressions and we're going to put them equal to each other since they're both y equals. Then I'm going to move all my terms over so that they are on one side. So I have this -9x, so I'm going to add positive 9x, -3, and then I'm going to add 5, and that puts all my terms onto the left-hand side. And now I can simplify this. So I have 2x squared plus -5 plus 9, which is 4x, and -3 plus 5, which is a +2, equals 0. And from here, I want to factor it. So let me just put both equations equal to each other. Move all terms onto one side. Collect like terms. And from here, we need to solve for x. So one of two things are going to happen. Either you can factor it, or you can use the quadratic formula. Your choice. All right, I'm going to go ahead and factor this, though. I can see that I have a 2, a 4, and a 2, so I can take out a 2, which would leave me with x squared plus 2x plus 1. And then two numbers that multiply to 1 but add together give me 2 are going to be x plus 1, x plus 1. So I get x equals -1 and x equals -1 again. So I don't have to write them both because it's considered to be redundant. So I just have to put it once. X equals -1. So that is the x coordinate of my point of intersection. So x coordinate of POI. Now I need my y coordinate. So I'm going to go back to my two original equations. I can use either one. I'm going to use my linear one because the linear one should be easier to use. And wherever there's an x, I'm going to put in a -1. -9 times -1 is +9. And it gives me 4. So that is my y coordinate. Of the point of intersection, which means now I have my point of intersection, which is at -1, 4. Now you can always do a check to make sure that this is your point of intersection. You could put this as an x and put this as a y into both of your equations, and you should get the same the same value on left side and right side. So you can always do a check. But here's kind of our method. We're going to put both equations equal to each other, and then we're going to move all our terms onto one side, collect like terms, and then factor it, or use a quadratic formula. That will give you your x coordinate of your point of intersection once you do that. And then from there, you want to put that number back into one of your two equations in order to get your y coordinate of your point of intersection. Okay. I think this is, if a line with slope 4 has only one point of intersection with the function y equals 0.5 x squared plus 2x minus 8, what is the y-intercept of the line? Okay. So we have a function. We have a linear function because line. So we have y equals 4x plus b. Now, the reason why I'm putting a b is because that's what we're trying to figure out, our y-intercept of the line. And then I have this other quadratic function. So 0.5 x squared plus 2x minus 8. So let's put these two equal to each other. And I know it seems weird because we're still trying to solve for b, but that's okay. We're going to move everything over onto the same side. So I'm going to subtract 4x, subtract 4x, subtract b, subtract b. And what I get is 0.5 x squared, 0.5 x squared, 2x minus 4x is minus 2x, minus 8 minus b equals 0. Okay, so we're looking to solve for b. So we know that there's only one point of intersection, which means that there's only one solution to this equation. Now, do you remember from, it must have been a couple of lessons ago, but we talked about when we have one solution, what we can use with a quadratic to help us when there's one solution, and that is the discriminant. B squared minus 4ac equals 0 when there's one solution. So let me go back. My a value is 0.5. My b value is -2. And my c value is this whole thing. So -8 minus b. I can plug all that information into my discriminant, -2 squared minus 4ac. And if it equals out to 0, then it has one solution. So -2 squared is 4. -4 times -5 is -2. So this is going to be -2 times -8 minus b. And then I'm going to multiply that -2 inside. So 4 plus 16 plus 2b equals 0. 4 plus 16 is 20. I'm going to move that 20 to the other side, becomes -20. Divide by 2, divide by 2, b equals -10. So then what is my y-intercept of the line? Well, my y-intercept equals -10. Okay, so this is where we took our linear and we were missing a piece of information. We put it equal to our quadratic, moved everything over onto one side. And then because it told me it only had one point of intersection, so therefore only one solution to this equation, I knew I could use my discriminant in order to solve for that. B squared minus 4ac equals 0 means there's only one solution. Once I plugged all those numbers in, it was just a matter of solving for b. It's a great question. Okay, practice this stuff. So you're going to take your two functions, put them equal to each other, the linear and the quadratic, Move all your terms onto one side, collect your like terms, and then from there factor it or use your quadratic formula to solve for x. Once you have your x value, you plug it back in and get your y value. Perfect. All right. As always, if you have any questions, please make sure you reach out.